Okay, so now let's turn our focus on a current loop. So we've seen now that if I apply, or if I have a current moving through a wire within a magnetic field, then I will feel a force. Now, it could be very practical if we could use that force in order to turn something or to make something move. And the obvious application of that is going to be in an electric motor. And so before we look at an electric motor, let's first look at a current loop. So let's say that I have a loop of wire here. That loop of wire, the current moves in this direction. And then I have a magnetic field here that moves from left to right. All right, and I want to know now what is the magnetic force on these various parts of the loop. Well, let's first focus on these portions of the loop. These portions of length A that run either parallel or anti-parallel to the magnetic field. Well, I know that force is equal to ILB sine theta. In this case, I would be the current, L would be the length A for the wire, V would be the magnitude of the magnetic field, and then theta in this case would be 0 degrees here and 180 degrees here. And both the sine of 0 and of 180 are both equal to 0, and so this force is equal to 0 newtons. There is no force exerted onto the loop on side A. But if we look at the loop on side B, I can imagine the force here, if I let my fingers go in the direction of I, B is to the right, and so on this side, on the left side, my magnetic field, or excuse me, my magnetic force is going to come out of the page. And then similarly, on the other side, if I use my right-hand rule as we've been, my force will be going into the page. So I will get a force that is acting on those portions of the current loop, actually creating a torque and causing this loop to rotate about this axis. So let's first just calculate what is the magnitude of that force. We'll just look at the force on one side. So we'll take this force, for example. What F is equal to ILB, sine of the angle theta. In this case, our angle theta is 90 degrees, and of course the sine of 90 degrees is equal to 1. So it's just going to be I times the length of the wire, which is little b. That's the length of this side of the wire, as we see it's b, times the magnitude of the magnetic field. Now, what is the direction of the force on the left-hand side and on the right-hand side? I've already shown this. You can use your right-hand rule. And if you want to pause here, just sort of step through this. Let your fingers go in the direction of I. They fold towards B, and the magnetic field comes out of your palm, and your thumb gives the direction of the force. So on the left-hand side, the force comes out of the page. On the right-hand side, the force goes into the page. All right, so the left-hand side out of the page, right-hand side into the page as drawn on the figure above. Okay, now we want to calculate the torque. So, first of all, let's see, the forces on either side of the loop are equal in magnitude. Same current, same length, are equal in magnitude. Same magnetic field. So they're going to be the same forces. They're opposite in direction, of course, but equal in magnitude. So now we can calculate the torque. Now remember, torque, in fact, on this one, we're going to have the torque on the left-hand side plus the torque on the right-hand side. Now, if you recall torque from last semester, torque is the product of the force times the length of the moment arm times the sine of the angle between those two. In this case, the angle between the force and the moment arm, the force is the magnetic force, the moment arm is the wire, or excuse me, is half the distance A. Let me go back and show you this. So I have this force acting here, and my moment arm is going to be this distance, the length from where the force is applied to where the axis of rotation is. So that's going to be the length of my moment arm. Now notice this total distance is A, so R then will equal A divided by 2. And that's going to be the case for both. Also notice the angle between the force and the moment arm. On the left-hand side, the force is coming out of the page, and the moment arm is towards the center of the axis, and so that angle is always going to be 90 degrees. So I can come back here. My torque, again, this angle is 90 degrees. I have an expression for the force here. That expression that we've already found is I times the length of the coil on side B times the magnetic field B times A divided by 2, where A divided by 2 is just the length of the moment arm. On the right-hand side, we're again to the same torque, IBB, A over 2. And so if I add these two together, I get IB, I'm going to rewrite this just a little bit, IB A times big B. So here, this is actually our area. So the area of the loop is the width on one side times the width on the other side, B times A. So if I wanted to rewrite the torque, and this is actually in your equation sheet, it's just going to be the current times the magnetic field, the strength of the magnetic field, times the area, where the area is just this B times A. This, by the way, will also hold for circular loops. So if you have a circular loop like this, it's also going to feel a torque that is calculated in this way, though of course for the area, instead of doing A times B, you do pi r squared. So that general formula holds up for any shape, whether it's a rectangular coil or square coil or pentagonal coil or a circular coil, which is more common. Now if you have multiple turns of wire, as you might expect, this expression is just for a single turn of wire, but if you have multiple turns of wire in, then our torque is just multiplied by that factor n. So the torque is equal to n, the number of turns of wire, times I times B times A. All right, here's a question about the current is flowing through this coil. So here I have the current flowing into the page, and over here I have the current flowing out of the page. Now it's in a permanent magnet, and so the magnetic field is going to run from north to south. So if I just consider this left-hand side, I'll get you set up on this a little bit. The current here is out of the page. This is looking at this left-hand side, and the magnetic field is in this direction. So what is the force on that side of the coil? And then you want to ask yourself, what direction does that force cause the coil to turn? Now, whatever the force is, the force on the other side is just going to be 180 degrees, anti-parallel to that, because both forces will cause it to move in a direction that is consistent with the other force. We'll make it rotate in the same direction. All right, we'll come back to this and we'll talk about electric motors in just a bit, but obviously this has close application to electric motors. So let's pause there.